All right, trust you did well on your quiz. Students in here felt somewhat confident, differing degrees of confidence. We had felt really good, felt pretty good, and then felt I'd like to feel good. We'll take a look at them in our next lesson. Let's go ahead and go on to our next chapter then, chapter 10. And we're going to circle back here a little bit to a type of motion that is still in a way translational motion, because there is a change in position, but with this motion there's always a return to the original position. And so two types of motion specifically studied here in chapter 10, circular and periodic motion, where although there's a change in location, there's a return to location constantly. And so the net result may or may not actually be a change of position. It's also not rectilinear motion at this point. Okay, so kind of moving off of rectilinear motion and forces that cause that into circular and periodic motion. First term I want you to get down in your notes is this term uniform circular motion. Uniform circular motion. Uniform simply means consistent throughout, all things being the same. There is a sameness to uniform, like the school uniform, right? You all pretty much wear the same thing to school. I actually had a student comment to me the other day who come from a public school, how at the public school, you know, different kids wearing the designer clothing, and then you got the kids wearing the Walmart clothing, and the rich kids picking on the poor kids and stuff. Like, well, you don't have to worry about that at Grace because everybody's wearing the same thing. We don't know if you're rich or poor. So anyway, because we all look the same. That's what uniform means. It's a sameness. Circular has the idea of going in a circle. So it makes sense then that uniform circular motion is motion that is in a circular path and at a constant speed. Motion that's in a circular path and at a constant speed. Now, circular motion in general refers to going around in a circle. Uniform circular motion is specifically that latter part where there's a constant speed throughout. But I want you to think about the word speed. We don't use that word very often. Normally we would use, class, the word velocity. Why a constant speed? Well, picture this. As an object goes around in a circular path, its direction is constantly changing, isn't it? For instance, at any point here, for instance, the object, let's just say it's a little ant walking around the circle. The ant is looking this way, but later on the ant is now looking that way, and then the ant is looking that way. You get the idea? The direction is constantly changing, and since velocity is speed in a particular direction, you can't have a constant velocity if the object is moving in a circular path. That's impossible. But it can move at a constant speed. But the velocity is always changing. Now hold on. What do we call a change in velocity? Acceleration, right? Now usually when we think of acceleration, we think of speed up, slow down, right? But this is a form of acceleration that isn't speed up or slow down. It's simply a directional change type acceleration. So an object that is in uniform circular motion is always accelerating, yet never speeding up. How is that possible? Well, we understand this idea of components, right? That which is x doesn't impact that which is y, correct? Now, that which is at an angle, both x and y, is a little bit of both, but that which is y doesn't affect x, right? Remember we said if you throw a baseball horizontally, there is gravity pulling down, but that doesn't affect the horizontal flight of the baseball. So then, if this acceleration were to act perpendicularly to the speed, then it wouldn't actually change the speed, would it? Right? Now think about it. The speed is how fast the object is going. Its direction is defined, Michael, you haven't learned this yet in geometry, by something called the tangent line. A tangent line is a line that touches a circle at only one point. Basically, these lines are little tangent lines. So I'm going to have to rely on you two for this. What is always perpendicular to a tangent? I believe it's theorem 39. My memory, it was just such a foundational theorem in our geometry class. Tangent, the word is clang, perpendicular to a radius or diameter at the point of tangency, right? So therefore, conversely then, or we could think the tangent's perpendicular to the radius, this acceleration, if it's perpendicular to the speed, then it must be going toward the center of the circle at all times. So this acceleration is always toward the center of that circular path. That way it doesn't actually speed up the object in any way. The object is traveling at a constant speed. Its acceleration is toward the center, and we call this, write this term down, centripetal acceleration. Centripetal acceleration. So the word centripetal actually means center seeking or toward the center. Now the object isn't moving toward the center, but there is an acceleration toward the center of the circle. Centripetal acceleration is notated A sub C. Acceleration with the sub C for centripetal. And the centripetal acceleration is equal to the square of the speed. Now I'm going to use V for velocity, but we understand the velocity is not actually constant. Velocity represents the speed divided by the radius. Basically this, the smaller the radius, the greater the centripetal acceleration, the greater pull there is, if you will, toward the center. The faster the speed there is, the greater the pull toward the center, but the speed matters more than the radius or the distance from the center. Think of it this way. You ever driven around a turn? A couple things would make the turn easier to navigate. Number one, if the turn were just wider. Still the same circular path, right? We think of the cloverleaf things around Columbus at the bypass, all those circular turns. Well, if they were a little wider, that would make them easier to navigate. Or if you, I don't know, something radical like, say, slow down, right? The slowdown is going to have a much greater effect on the centripetal acceleration that you feel versus the radius, but they both have an impact. But I keep mentioning a pull toward the center. Well, that's because you can't have acceleration per Sir Isaac Newton's first law of inertia. You won't have an acceleration or a change in velocity without some external force. So in order to have acceleration toward the center, in order to have centripetal acceleration, there must be some centripetal force that's pulling toward the center. We call the force that causes centripetal acceleration centripetal force. So the force toward the center of the circle is called centripetal force. Like I should have saw that coming. Right. And how do we find force per Newton's second law of motion? Centripetal force is the force toward the center. How do we find centripetal, or how do we find force in general per the second law, class? Not mass over acceleration. Mass times acceleration. F equals ma. We, in the last, with the problems, we kept doing A, stay with me, A equals F over M, but F equals ma. Well, that means that centripetal force equals mass times this. So M V squared over R. And that's why I say that the pull toward the center, or that weird feeling you feel when you go around a turn, will be mitigated really three ways. Number one, if it were a wider turn, you wouldn't feel it as hard. Smaller turn, you're going to feel it much more strongly because it's inversely related to the radius. Speeding up and slowing down is the biggest effect by far, but also the greater the mass, the greater force is needed to keep pulling it in toward the center. And tomorrow we're going to look at some specific types of forces that will act as centripetal forces. I put your homework on the board at the end of the quiz. We already should have it copied down, but just in case we missed it, homework is to read pages 144 to 147, and on page 156, answer questions 1, 2, 4, and 5. Have a wonderful rest of your day, and you are dismissed.